Hello, everyone. My name is Will Creighton. I'm a postdoctoral researcher at Brown University, where I study the human factors of programming. And this talk is about a longitudinal study of how people learn Rust, done in collaboration with my colleagues Gavin Gray at ETH Zurich and Sriram Krishnamurthy at Brown. And folks, let me just start off by telling you, we've figured it out. We have unlocked the key to whether someone truly understands Rust. And it turns out you only need one question. This is the hardest question we could come up with. Without further ado, here it is. Consider a program with the following unit tests. What is the shortest string you can pass to cargo test such that only test the logger and test the database and not test logger and database are executed? You might think I'm joking, but of all the questions about Rust we've asked people, this is the single hardest of them all. Only 8% of Rustaceans will get it right on the first try. But as you probably understand, just because a person can compute the discriminating substring in their head, it doesn't mean they understand Rust. Or put another way, if you taught someone to master this specific problem, that doesn't mean that same person can go off and write a production-grade system in Rust. Learning Rust is just not that easy. So let's zoom out for a second and talk about the broader context of the study. The problem, put simply, is that Rust is not an easy language to learn, and I'm sure some of you are thinking like, all right, that's the understatement of the century. But the Rust developers know this, right? The Rust 2024 roadmap explicitly put flattening the learning curve as a major goal. But operationally, like, how do you just sit down and make Rust easier to learn? I mean, plenty of people have tried to write textbooks, tutorials, exercises, YouTube series. How are you going to do better than all of them? And while one way is to be scientific, we can gather data about where people are struggling and then target those specific areas. And in fact, the Rust 2020 survey already did a lightweight version of this idea. They asked several thousand Rustaceans which topics they found difficult on the x-axis and counted the results on the y-axis. And sort of the usual suspects emerge. You have lifetimes, ownership, macros, trait bounds, async, unsafe, all that good stuff. And this is helpful, but it's not very precise. Like, what is it about, say, ownership that people struggle with? And so the core idea in this experiment is that we gathered fine-grained data about learners' struggles with Rust using quiz questions. So we took the Rust programming language, pictured here, which is the main open source textbook that people use to learn Rust. And we inserted these little quizzes throughout the entire book. So if a reader clicks the quiz, then they're presented with short answer or multiple choice questions about what they just learned. Like, the keyword for declaring a new function in Rust is blank. And after completing the quiz, the reader gets feedback on their responses. You know, you answered FUNC, but the correct answer is FN. In total, I wrote about 150 quiz questions placed throughout all 20 chapters of the Rust book. Carol Nichols very graciously agreed to put this advertisement for our experiment in the actual Rust book, which went live about 10 months ago in November of 2022. And since then, we've had over 50,000 people read our version of the book, and they've answered questions over 1 million times. So we have a big data set, a very chunky SQLite file of people's experiences learning Rust. And I'm going to talk about what we learned from this data in 3 steps. What questions did people find difficult? How can we help people improve on those individual tough questions? And third, how can we help people with broader categories of questions, like ownership? So first, let's get acquainted with the data set. Which questions did people find easy and hard? All right, here's an easy one. This question asks, determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. And the program has a function foo that prints a reference to an i32, no problem. But then in the main function, we say let x equals null. And Rust does not make it that easy to build a null pointer. So the correct answer would be to say this program does not compile. And in fact, 100% of our readers get this right. Yeah, people understand. Yeah, Shout out to Rust learners. They get that this function doesn't compile. That's good. Basic safety guarantees. Here's a more difficult one. Again, same format. Tell me if this program compiles or doesn't, and we'll read through it. So this program creates a vector v of numbers 1, 2, and 3. It creates a vector v2 of mutable references to numbers. We iterate over v to add mutable references to each element into v2. And then we mutate v20 to be 5 instead of 1. Finally, we read v20 and v0 and print them out. Okay, so a more subtle question involving data structures, mutable references, borrow checking. Hopefully you think about it a little bit, what you think the answer is. And we can take a look at the distribution of responses to this question. So 33% of readers incorrectly say that this program doesn't compile, probably thinking that there might be a lifetime conflict, but this does actually compile in part due to non-lexical lifetimes. 36% of readers incorrectly say this program prints out 5, 1, meaning they think that the mutation on v2 does not affect v. But only 24% of readers correctly say that the output is 5, 5. And there's a 7% long tail of other answers, but these are the 3 common cases. And so this problem shows that people struggle to understand when it's safe to pass around mutable references to something, and to understand when those mutation of those references can cause action at a distance. Okay, and so hopefully these examples give you a sense of the kinds of questions we asked and the range of responses we can get. I obviously can't go through all 150 questions. Instead, I'll briefly discuss some interesting patterns that we saw in the data. So one is that readers tend to have a very narrow conception of what unsafe code is for. Like unsafe is only for foreign function interfaces, or unsafe is only for mutably accessing independent fields of an array. I think people don't get how limited the borrow checker is in some ways, or conversely, how many use cases exist for unsafe or abstractions built on unsafe. Readers don't really understand what the borrow checker is protecting you from. Like, very few people have a conception of undefined behavior, double freeze, null pointer dereferences, that sort of thing. And a really important factor here is that in 2023, the people learning Rust are not coming to the language already being low-level systems hackers. So in one of our surveys, we found that 58% of Rust learners do not consider themselves proficient in either C or C++. And so Rust learning resources have to do double duty as both an intro to Rust and an intro to systems programming for many people. I think readers don't really understand the limitations that are placed on trait objects, often saying things like they think they have better developer ergonomics than just using plain generics, which I would consider broadly not to be true. And when it comes to performance, for instance, when we ask how many allocations could occur in something like a string program, people often underestimate the number of allocations in the program. I think readers really struggle to predict the potential memory usage of their code just reading its source. Readers also struggle with module trees that are not straightforward. In particular, when you change the topology of the module tree using re-exports, problems involving that are very challenging for readers. And also just anecdotally, I've talked to many Rust learners who say, I have no idea when to use self, super, crate, and all the various keywords involved in using modules. So these are 5 points I found insightful. And returning to the high-level point, I think these quiz questions have been successful at pointing to the struggles of Rust learners with a greater degree of specificity than just ownership is hard or traits are hard. Like, these are more actionable items if we want to address them in the textbook. So that brings me to part 2. Once we gathered some initial data on the easy and hard parts of the Rust book, we decided to intervene. We could take the hardest problems and change the content of the book to address whatever we think is tripping up readers. And I think this approach was overall quite successful. So here's one example, and again, we'll walk through it. In this problem, you have a generic point type, point of t, with fields x and y. You implement a method f for a specific type, point of i32, that returns a field like self.y. Then you also implement the same method for all types t, except it returns self.x. And then we ask, if you try and call f on some point p, what does it return? And the answer is that this doesn't compile. Rust does not allow conflicting implementations like this. But when we ask Rust learners this question, after teaching them about generics, only 29% of them answer correctly. And I think these learners are probably carrying over a misconception that Rust has a concept of inheritance, like in object-oriented languages, or maybe a concept of specificity, like in cascading style sheets. But stable Rust does not have either of those things, at least not yet. And so after seeing poor performance on this question, I reread the chapter and I realized that this aspect was just never really addressed. So I wrote a small paragraph explaining that Rust doesn't have inheritance. You don't have to read it. I want to emphasize this is the entirety of what I changed, is what's on the slide. And adding just this one paragraph was enough to improve average performance from 29% to 74% on this question. So hey, that's pretty cool. We saw a problem, we deployed a fix, and we saw an improvement from the fix. I mean, that is the heart of taking a scientific approach to the design of learning materials. Now, of course, this is not a fully mechanical process. How did I know to come up with this question? How did I know to write this specific paragraph? That was just my intuition as an educator and a longtime Rust user. But the science helps us know that this intervention was needed and that it succeeded, but it was an art to make the intervention in the first place. And we can also get a sense of this tension by looking at a change that didn't work. So this question asks, why would someone use a procedural macro over a declarative macro? And a common incorrect answer is this second bullet, that a macro requires an entire item as input. Declarative macros can also take items as input, so it's not really a standalone reason to use a procedural macro. To address the issue, I added this sentence to the section on macros, and it says, for example, declarative macros can match against expressions, types, and even entire items. But once we deployed this, it had no effect. There was a 1% increase in performance, but it was not statistically significant, so most likely just noise in the data. And this is where the iterative loop gets hard. Why didn't this work? One reason might be that the paragraph is pretty far from where the question got asked. Readers might have skimmed over it and just forgotten it by the time they reached the question. Or maybe the sentence isn't enough to correct whatever misconception caused the wrong answer. A person might read this and think, well, okay, declarative macro could take an item as input, but it wouldn't make sense to. Or maybe the question itself is poorly worded. People think reasons are valid for different reasons than I do. And this is another place where the science gives way to art. It takes creativity and empathy to kind of figure out just the right way to ask a question or patch up a misconception. But besides this case, overall, the interventions were quite successful. Out of 14, 12 made a statistically significant improvement in accuracy on the question being targeted. And by the way, statistical significance means the change in accuracy is not likely to just be noise in the data. It's more likely to be attributable to the change that I made. And the average size of these significant effects was an increase in accuracy by 19%. I think that's pretty good. That's 2 letter grades of improvement. And thankfully, there were no negative effects. I didn't manage to make anyone worse with these interventions. Now, of course, this doesn't mean 85% of all possible interventions will succeed. There's selection bias. I only tried the interventions I thought would work. But it does demonstrate that it's possible to establish a causal connection between changes to the textbook and learning outcomes. You just don't have to guess whether a change is good or bad. You can see its actual effect in the data. And so this approach of going question by question is good for small-scale concepts. But it's not really sufficient for bigger concepts in the language. And so in the last part of the experiment, we zoomed out to look at how people understand one of the most famously hard parts of Rust, ownership. We asked, what is it about ownership that people find difficult, and how could we make it easier? This part on its own was quite a large endeavor. We wrote a whole 30-page academic paper about it that's now up on arXiv. It's in tiny text at the bottom, or you can check it out on my Twitter feed. But I'll give you a high-level overview of our process in the rest of this talk. So in the first step, we ran a formative study to better understand why people struggle with ownership. We used Stack Overflow to gather a data set of common questions that Rust learners ask about ownership. This is a screenshot of the top questions tagged with Rust. And for example, a question would be something like, is it possible to return either a borrowed type or an owned type in Rust? And then we would extract a simplified version of the code involved as an example of the situation. So here, this makeSeparator function is invalid. It does not compile. It wants to return a reference to a string and stir, but it unsafely returns a reference to an owned string on the stack. And the idea is that this snippet exemplifies a common situation where Rust learners struggle with ownership. We found 8 situations just like this one, and we developed a test where we give a Rust learner this program and ask them 3 questions. What error would Rust give for this program? If Rust allowed this program to compile, what is an input that would cause undefined behavior? Think carefully about that question. And third, how would you idiomatically fix this function? And the idea is that these 3 questions represent different stages of reasoning about ownership. The first asks, do you understand ownership in the type system? The second, do you understand ownership at runtime? And the third, do you understand ownership in terms of program architecture or design? And after analyzing the responses of 36 Rust learners, we found a couple of trends. First, Rust learners can usually guess the surface reason that the compiler will reject a program. So people know that you can't have 2 mutable pointers to the same data, for instance. But they struggle to explain what will go wrong if the compiler accepted a bad program. Like, why can't you have 2 mutable pointers to the same data? And the key idea is that lacking this deeper understanding led to issues down the road in trying to construct idiomatic fixes. And so our takeaway was that we needed to change the Rust book to give people a more solid foundation in how Rust works at both compile time and runtime. And in particular, the key to understanding ownership is memory. The stack, the heap, pointers, allocation, freeing, boxes, references, all that good stuff. And so the first thing we did is to develop a tool to take a Rust program and automatically visualize the state of memory at each point. So I'll show you an example. So this program doesn't actually compile. It's meant to illustrate an example of undefined behavior. Let's walk through it. First, we create a vector vec with the numbers 1, 2, and 3. Then we create a reference num to and vec2. And after this statement, we see the contents of memory at L1 in the diagram. So the contents of the vector is allocated on the heap, and the vec variable on the stack points to the beginning, and the num variable points to the number 3. Then we do vec.push4. This causes the vector to resize its heap allocation, freeing the previous one to make space for the new element. The vector then contains 1, 2, 3, and 4. And in the process, the reference num has been invalidated. It points to deallocated memory. And finally, if we try to use num by reading it in the print line, we get undefined behavior. We used a pointer after its pointee is freed. And so in terms of ownership, this diagram helps a Rust learner see the organization of memory into a stack and a heap, and see the various pointers between the 2 regions. By simulating the program, it helps a Rust learner understand the underlying reason why the borrow checker would reject a program. But the diagram doesn't still explain how the borrow checker works. So we needed to develop a different kind of diagram for that. This diagram visualizes the changes in the state of the borrow checker after each statement. Again, let's walk through it. We have a program that's similar as before, but this one actually does compile. It's a safe program. Again, we create a vector vec with the elements 1, 2, and 3. And this little box on the right tells us that the variable vec has gained 3 permissions: read, write, and own. And the idea of permissions is really the central metaphor that we use to explain how the borrow checker works. Vec is readable, like you can get its length, for instance. Vec is writable, you can add an element to it. And Vec is ownable, meaning you can move it or drop it. And on the next line, when we make a reference, num equals and vec2, this does a couple of things. First, it removes the write and own permission from vec. So that means we cannot mutate or drop the vector while the reference is being used. Second, it creates permissions for num, the reference, and star num, the data accessed through the reference. Because this is an immutable reference, we only have read permissions on star num and not write permissions. Once num is no longer used after the print line, then vec regains its write and own permissions, and num and star num lose all of their permissions. And this shows the idea of non-lexical lifetimes, that the transfer of permissions is related to the ranges of code where a reference is used, and not based just on syntactic scopes. And finally, we're allowed to push to vec on the next line, and then vec loses its permissions. And so the goal of this diagram is to give Rust learners a first principles approach to borrow checking. Rather than learning ownership as a bag of heuristics, like I can't have two overlapping mutable references, instead the permissions metaphor gives the Rust learner a deeper way to see these heuristics as instances of a principle as opposed to one-off rules. And another key idea behind both of these visualizations is that they can show learners the states of systems that were previously either invisible or difficult to talk about. Like normally, learners only encounter the borrow checker when they do something wrong and the compiler yells at you. But with this diagram, you can see how the borrow checker is working even for a totally valid program, like this one. Conversely, when the borrow checker does yell at you, you can't run the program and see why the borrow checker is complaining, but our runtime visualization allows you to do just that through simulation. And so with these two tools, we developed an alternative ownership chapter for the Rust book. We reworked the pedagogy to give readers a clear mental model of what a pointer is, how pointers work in Rust, the stack versus the heap, how the borrow checker catches undefined behavior, and so on. We used the diagrams to illustrate these ideas at each point. Again, you don't have to read all the text. The screenshot just gives you a sense of what these diagrams look like embedded into the textbook. And so normally in educational practice, we would just toss the book out into the wild and see what people say and sort of hope for the best. But we're here to do science. And so we wanted to evaluate the effect of the permissions pedagogy. In order to do that, we need a measurement. Did it work? How can we tell if this is helping people? So we made a test of how well people understand ownership. And we reused the same questions I mentioned earlier. So we take a situation from Stack Overflow, like the function that returns the reference to stack allocated data. And then we ask a question. If the compiler allows this function to compile, select every call to the function that would cause undefined behavior. That's how we make it multiple choice rather than open-ended. And one cool little detail here is the incorrect answers, or distractors, are actually just the most common misconceptions that people had in the original study. They're not totally arbitrary, they're taken from data as well. And so in total, we made 24 questions out of these 8 tricky situations and called it the ownership inventory. To establish a baseline, or like a control condition, we first deployed the inventory when people were reading the same ownership chapter that exists in the current Rust book. And the average score for these learners was 47%. Then we deployed our pedagogy, and it went up to 56%. All right, that's pretty good. Yeah, plus 9%. Thank you. Okay, there's room for improvement, but like the data shows, this pedagogy helps. It's a step in the right direction. There are caveats in interpreting this. For instance, one is that I developed the test and was aware of it when I wrote my version of the textbook, and the original Rust book authors were not. So it's not a fully fair comparison. And another caveat is that the new pedagogy is more complex than the old one. Like I saw recently a post on the Learn Rust subreddit that was like, hey, isn't this new chapter way more complicated than the old one? And I was like, oh, okay, yeah, it's a little more complicated. But I think, of course, the complexity is warranted, that it's part of the intrinsic part of learning Rust and not something you should put off to later. But it is true that this pedagogy front loads some of that complexity. And so the point is, right, the science gives us numbers for us to compare, right? But it's ultimately an art to say, what do those numbers mean? And the best way to do that is to go read the book. The quiz, you can check out the quiz questions, experience the pedagogy. Our experimental book is still live at rust-book.cs.brown.edu. And so I encourage you all to check it out. Also, it's linked to from the actual Rust book if you forget the URL. Additionally, all of the technology described in this talk is open source at our GitHub organization, Cognitive Engineering Lab. You can check out the diagram generator, Aquascope, the book source at RustBook, and the quiz widget at MDBookQuiz. We are perfectly happy to accept contributions, especially for Aquascope and MDBookQuiz. For example, the runtime diagram I showed you, it has a ton of features I have not implemented yet because we just haven't had time to get around to it. So please, come help us build the future of tools for Rust education. All right, just to wrap up, here's a few of my main takeaways. First, I think that adding quizzes to the Rust book has just been a total success. It's a kind of simple idea. It doesn't take that long to write the quizzes. Readers love having these quizzes. That's the reason they flocked to our book, is just to take the quizzes. And the data is super valuable in understanding the learning curve of the language at a finer grain level. Second, the hard parts of Rust aren't just ownership. There's all kinds of subtleties about how import paths interact with re-exports, where operations perform heap allocations, how semantic versioning works in cargo. All of this kind of stuff is difficult for Rust learners. And so people who develop Rust learning resources have to keep a very broad view on what skills Rust stations need to be effective. And third, most learning resources are just text and code snippets with the very occasional diagram that often takes a long time to draw in Illustrator or generate with GraphViz. But I think that if people develop the right visualization tools, like, for instance, the diagram generators you saw, these can be really powerful aids in building a better pedagogy. All right, there's much more to say, but I'm out of time. So if you want to learn about any part of this experiment, please come talk to me, check out the website, you can read our paper, and otherwise, thank you for listening.